Quantum foam is a concept in quantum mechanics devised by John Wheeler in 1955. The foam is supposed to be conceptualized as the foundation of the fabric of the universe. Additionally, quantum foam can be used as a qualitative description of subatomic space-time turbulence at extremely small distances. At such small scales of time and space, the Heisenberg uncertainty principle allows energy to briefly decay into particles and antiparticles and then annihilate without violating physical conservation laws. As the scale of time and space being discussed shrinks, the energy of the virtual particles increases. According to Einstein's theory of general relativity, energy curves space-time. This suggests that at sufficiently small scale as the energy of these fluctuations would be large enough to cause significant departures from the smooth space-time seen at larger scales, giving space-time a foamy character. With an incomplete theory of quantum gravity, it is impossible to be certain what space-time would look like at these small scales, because existing theories of gravity do not give accurate predictions in that realm. Therefore, any of the developing theories of quantum gravity may improve our understanding of quantum foam as they are tested. However, observations of radiation from nearby quasars by Floyd Stecker of NASA's Goddard Space Flight Center have placed strong experimental limits on the possible violations of Einstein's special theory of relativity implied by the existence of quantum foam. Thus experimental evidence so far has given a range of values in which scientists can test for quantum foam. Experimental evidence: the MAGIC telescopes have detected that among gamma-ray photons arriving from the blazar Markarian 501, some photons at different energy levels arrived at different times, suggesting that some of the photons had moved more slowly and thus contradicting the theory of general relativity's notion of the speed of light being constant, a discrepancy which could be explained by the irregularity of quantum foam. More recent experiments were however unable to confirm the supposed variation on the speed of light due to graininess of space. Other experiments involving the polarization of light from distant gamma-ray bursts have also produced contradictory results. More Earth-based experiments are ongoing or proposed. Constraints and limits X-ray and gamma-ray observations of quasars use data from NASA unregistered trademark S. Chandra X-ray Observatory, the Fermi Gamma-Ray Space Telescope and ground-based gamma-ray observations from the Very Energetic Radiation Imaging Telescope Array show that space-time is uniform down to distances 1,000 times smaller than the nucleus of a hydrogen atom. Quantum mechanics predicts that space-time is not smooth, instead space-time would have a foamy, jittery nature and would consist of many small, ever-changing, regions in which space and time are not definite, but fluctuate. The predicted scale of space-time foam is about 10 times a billionth of the diameter of a hydrogen atom's nucleus, which cannot be measured directly. A foamy space-time would have limits on the accuracy with which distances can be measured because the size of the many quantum bubbles through which light travels will fluctuate. Depending on the space-time model used, the space-time uncertainties accumulate at different rates as light travels through the vast distances. Chandra's X-ray detection of quasars at distances of billions of light-years rules out the model where photons diffuse randomly through space-time foam, similar to light diffusing passing through fog. Measurements of quasars at shorter, gamma-ray wavelengths with Fermi, and shorter wavelengths with Veritas rule out a second model, called a holographic model with less diffusion. Relation to other theories, quantum foam is theorized to be the fabric of the universe, but cannot be observed yet because it is too small. Also, quantum foam is theorized to be created by virtual particles of very high energy. Virtual particles appear in quantum field theory, arising briefly and then annihilating during particle interactions in such a way that they affect the measured outputs of the interaction, even though the virtual particles are themselves space. These vacuum fluctuations affect the properties of the vacuum, giving it a non-zero energy known as vacuum energy, itself a type of zero-point energy. However, physicists are uncertain about the magnitude of this form of energy. The Casimir effect can also be understood in terms of the behavior of virtual particles in the empty space between two parallel plates. Ordinarily, quantum field theory does not deal with virtual particles of sufficient energy to curve spacetimes significantly, So quantum foam is a speculative extension of these concepts which imagines the consequences of such high-energy virtual particles at very short distances and times. Spin foam theory is a modern attempt to make Wheeler's idea quantitative. See also. Footnotes. References: John Archibald Wheeler with Kenneth Ford. Geons, Black Holes, and Quantum Foam 1995 ISBN 0-393-04642-7. Reginald T. Cale. Gravity as Quantum Foam in Flow. June 2003. Borrowed Time, interview with Michio Kaku, Scientific American, Sarup, a 2006, site set on quantum froth, New Scientist, 189, pages 18, Science Full Text Select, EBSCOhost, viewed February 10, 2012.